Welcome to Learn Algorithm Design and Analysis course. In this session, we focus on analysis of divide and conquer based matrix multiplication. In the previous session, we have seen that how to multiply two matrices using divide and conquer based method. We have devised the divide and conquer logic to multiply two matrices of orders n by n and n by n respectively. So given two matrices A and B, which are of orders n by n, such that the matrix order n is represented in this form: n is equal to 2 power k, where k greater than 0, this is the positive integer. So A is of order n by n, capital B is also of the same order n by n. When n is represented in this form, n is equal to 2 power k, we can multiply the two matrices A and B. The resultant matrix is C is equal to A into B. The resultant matrix is of order n by n. A is of order n by n, B is of order n by n, so the resultant matrix is of order n by n. Now, applying the divide and conquer logic, initial size of n by n, this is subdivided by 2, n by 2 by n by 2. Since C is equal to A into B, for example, A and B are of n by n matrices. Applying the divide and conquer logic, since n is equal to 2 power k, we are subdividing the matrices A and B in such a way that here the initial size n by n is reduced to n by 2 by n by 2. Here the order is n by 2 by n by 2. Here the order is n by 2 by n by 2. Here the order is n by 2 by n by 2. In the same way for matrix B, here the order is n by 2 by n by 2. This submatrix is of order n by 2 by n by 2. This submatrix is of order n by 2 by n by 2. And here this submatrix is also of order n by 2 by n by 2. Now having these 8 submatrices of order n by 2 by n by 2, we can multiply these matrices using the equation C is equal to A into B, assuming that each submatrix is denoted as A11, A12, A21, A22. Then for the matrix B, B11, B12, B21, B22. Then the resultant matrix C, that is C11, C12, C21, C22, are obtained by multiplying the matrices A and B. So clearly C11 is first row, the first column, multiplying the elements A11, B11 plus A12, B21, right? First row, first column, A11 into B11 plus A12 into B21. Then C12, this is first row and second column, A11, B12 plus A12, B22. Likewise, C21, this is second row, then first column, A21, B11 plus A22 into B21. Second row, first column elements are multiplied and added. Then C22 is obtained by taking here the second row, here the second column. So clearly C22 is A21 B12 plus A22 into B22. So now we have to think of each Aij and Bij, each Aij and Bij as the matrix of order n by 2 by n by 2. So using these equations, we can find the product of our two matrices A and B. When we multiply, say, A11 into B11, or simply write Aij into Bij for I is equal to 1 to 2 and j is equal to 1 to 2. In this case, since the product of two n by 2 by n by 2 matrices are also obtained by applying the divide and conquer logic. So recursively in the next stage, the matrices of orders n by 2 by n by 2, two matrices of orders n by 2 by n by 2 is subdivided by 2. That means n by 2 power 2 into n by 2 power 2. Then next stage, this order is further subdivided by 2, n by 2 power 3 into n by 2 power 3. So this goes on in the final stage when n by 2 power k into n by 2 power k is reached, such that we have assumed n is equal to 2 power k, so that n by 2 power k, n by 2 power k into n by 2 power k becomes n by n into n by n. That means 1 into 1. So in the final stage, when we reach a matrix A and B, capital A and capital B, such that A is having one element, one row, one column, A11, or simply A11, right? First row, first column. B, right? Say B11, first row, first column. As a matrix which consists of exactly one element, then we can find the product C is equal to simply A11 into B11. Because A and B are of 1 by 1 matrices, one row, one column in A, in B also one row, one column, so that the product of A and B is obtained and it is stored in the resultant value or resultant matrix C. So how long we are applying this divide and conquer logic? Initial size n by n, initial size here, this n by n, this is subdivided by 2, n by 2 by n by 2, then n by 2 power 2 into n by 2 power 2, etc. Final stage is n by 2 power k into n by 2 power k, such that n is equal to 2 power k. So we are subdividing this matrix by 2 until we reach a matrix of order 1 by 1. So when we reach a matrix of order 1 by 1, here the recursion terminates. So how long we are finding the repeated application of recursion? We are applying the repeated application of recursion until the matrix size is greater than or equal to 2, n by n, where each n, right, that n is greater than or equal to 2. Even when n is equal to 2, right, we have applied the divide and conquer logic. Then we have, right, each matrix of order 1 by 1, there we are finding the resultant value as C is equal to A11 into B11. Hence, if we say the computing time, which is represented using the notation T of n, assume that T of n, which represents the computing time of T of n, which represents the computing time of two n by n matrices multiplication by applying the divide and conquer logic. Since after subdividing the matrix n by n into n by 2 by n by 2 submatrices of orders, both in matrices A and B. Here we have 4 n by 2 by n by 2 matrices. Here we have 4 n by 2 by n by 2 matrices. These matrices are multiplied by applying the conventional logic as C is equal to A into B. In this case, the computation of Cij requires that 8 multiplications. For example, here A11 into B11, first multiplication. A12 A12 into B21, this is second multiplication. This is the third multiplication. This is fourth multiplication. This is the fifth multiplication. Sixth multiplication. This is seventh multiplication. This is eighth multiplication. So clearly 8 multiplications are performed here and 1, 2, 3, 4 additions are performed. 8 multiplications and 4 additions are performed here. Now let's include the count of 8 multiplications and 4 additions here so that the computational time T of n, this is represented as 8 into T of n by 2 plus A into n square. This is true when n is greater than or equal to 2. Because the computing time of two n by n matrices are given as T of n. After subdividing n by n into n by 2 by n by 2, we need to find the computing time of 8 matrices multiplication which are of orders n by 2 by n by 2. So recursively we are defining the computational time as T of n is equal to 8 into T of n by 2 plus A into n square. This is true when n is greater than or equal to 2. And a constant say C, right? This is the case when n is less than 2, or you can take n is equal to 1. This is the recurrence relation along with the termination condition T of n is equal to C when the input size reaches 1 by 1 order. Clearly the function name T is available in the right hand side of the equation, right? Here T, here also T. So function calls itself as a recursion. The recurrence relation is defined. Since matrix multiplication computational time is recursively defined as here 8 into T of n by 2 and 2 n by n matrices are added using the computational complexity of theta of n square computational complexity. So for a fixed number of additions, we have a cost A, then the computational time is n square. That's what this is 8 into T of n by 2. This is added with A into n square. Now this recurrence relation, this is the recurrence relation. This recurrence relation is solved by applying the substitution method. Now let's apply the substitution method. Applying substitution method to solve this recurrence relation, writing T of n is equal to 8 into T of n by 2 plus A into n square This is true when n is greater than or equal to 2. Now, this recurrence relation involves finding the value t of n by 2. So, to find a value t of n by 2, here we need to put n is equal to n by 2 in equation 1 so that t of n by 2 is obtained. 8 into put n is equal to n by 2, n is equal to n by 2 in equation 1. We have t of n by 2. So in the left hand side, the function name is t of n. Substitute n is equal to n by 2. We have this is equal to 8 into t of n by 2 by 2. That is n by 4. Let's write as n by 2 power 2. Plus a into n square. This term. Substitute n is equal to n by 2. We have a into n by 2 the whole square plus additionally we have a n square. So writing this is a n square. Simplifying this equation, right, one step further, this is equal to 8 into 8, 8 square. This is t of n by 2 power 2 plus this is a n square by 4. Let's write this is 8 by 4 into a n square plus a n square. Extending the recurrence relation one more stage, let's find the value of t of n by 2 power 2 here, t of n by 2 power 2. So to find t of n by 2 power 2, here in equation 1, substitute n is equal to n by 2 power 2. Substituting n is equal to n divided by 2 power 2 in 1. We have the next stage simplification. T of n is equal to what is available in the right hand side, 8 square into this is 8 square into t of n by 2 power 2. T of n is 8 into t of n by 2 plus a n square. Putting n is equal to n by 2 power 2, we have 8 into t of n by 2. Already n by 2 power 2 is there. N by 2 power 2 is divided by 2 to have n by 2 power 3. Plus a into n square. So writing here plus a n square. N is n by 2 power 2 whole square. That's all. Since n is equal to n by 2 power 2, substituting a into n square, that becomes a into n by 2 power 2 whole square. Plus additionally we have these two terms, 8 by 4 a n square plus a n square. Let's write as it is, plus 8 by 4 a n square plus a into n square. Now simplifying this recurrence relation one step further, 8 square into 8 becomes 8 power 3 into t of this is n by 2 power 3 plus this is a n square by a 2 square, right, 4 square. We can write this is a into n by 4 the whole square. So simplifying here, this is already multiplied with a value 8 square. So 8 square, we can write this is 8 by 4 whole square, right, 8 by 4 whole square into a n square. 8 square into a into n by 2 power 2 whole square becomes 8 by 4 whole square into a n square. Then remaining two terms, last two terms, 8 by 4 a n square plus 8 by 4 a n square plus a n square. These two terms are written as it is. Now it seems this is continuing because initial stage this is 8 power 1 into t of n by 2 power 1. Next stage 8 square into t of n by 2 power 2. Then next stage this is 8 power 3 into t of n by 2 power 3. So to terminate a recursion, clearly the actual parameter of t, that should become 1. So to make the actual parameter as 1, the term, right, actual parameter, right, that means n by 2 power k, this should be equal to 1 such that n is equal to 2 power k. So denominator, as we explored earlier, first stage n by n, then n by 2 into n by 2, then n by 2 power 2 into n by 2 power 2. Final stage is n by 2 power k into n by 2 power k. So write last stage, when a t becomes a t of n divided by 2 power k, clearly the power of 8 is 3. Hope you understand. So the generalization is 8 power k into t of n by 2 power k plus. Now have a look into, right, the next term. If this is 8 power k, next term is 8 by 4 whole power k minus 1 into a n square. This is important because 8 power 3, previously 8 power 3 means here 8 by 4 whole square into a n square. Previously 8 square means this is 8 by 4 whole power 1 into a n square. So 8 square, 8 by 4 whole power 1 into a n square. 8 power 3, 8 by 4 whole square into a n square. 8 power k, that means 8 by 4 whole power k minus 1 into a n square, right? Plus etc. Last three terms are written as it is. 8 by 4 whole square into a n square plus 8 by 4 a n square plus a n square. Now we have the generalization. This can be simplified further. Now let's substitute k is equal to log n base 2. Since n is equal to 2 power k, taking log base 2 on both sides, log n base 2 is equal to log base 2 2 power k, that is k into log 2 base 2 becomes k. So wherever is k, alright, that k should be replaced using log n base 2. So here let's replace this is 8 power log n base 2 t of n by 2 power k. Substitute n is equal to 2 power k. This becomes 8 power n by 2 power k. That means n by 2 power k, that is 1. So t of 1 plus. Remaining terms need to be simplified considering the common factor a n square. Considering the common factor a n square. So let's take a n square as the common term. This can be taken out. Remaining terms are right from right to left, right? This is 1 a n square. Let's write 1. Then this is 8 by 4. 8 by 4. Then 8 by 4 whole power 2. Then plus etc. 8 by 4 whole power k minus 1. Since a n square has the common factor is taken from each term. Now simplifying this, 8 power log n base 2, we can interchange in a power log log b base e. This is equal to b power log a base e. We can interchange a and b, whatever is the base. So here base is 2. Let's interchange this 8 and n so that we will get n cube. So n power log 8 base 2. T of 1 is a termination condition. When n becomes 1, T of 1 is a constant computational time. So substitute T of 1 is equal to C here. T of 1 is here C plus a n square into, this is written as 1 plus 8 by 4 2, then 2 square plus etc. Last term is 2 power k minus 1. 1 plus 2 plus 2 square plus etc. 2 power k minus 1. This is a geometric series that needs to be simplified. So we can simplify using the geometric series. Now n power log 8 base 2, this is equal to n power log 8 base 2, that 8 is written as 2 power 3 because 2 power 3 is 8, log base 2 8 is written as 2 power 3. This is multiplied by c, so we can write this into c plus a into n square. Remaining terms 1 plus x square plus etc. x power n, right? That is a geometric series. 1 plus x square plus etc. plus x power n is equal to x power n plus 1 minus 1 divided by x minus 1. Then the absolute value of common ratio is greater than 1. So applying this geometric series, here we have x is equal to 2. 1 plus 2 plus 2 square. So x is 2. 2 power k minus 1. Final right, x power is k minus 1. So here clearly n is k minus 1. X is 2 is k minus 1. K minus 1 corresponding term is here n. So replacing x power n plus 1 minus 1 divided by x minus 1, we have, this is 2 power n plus 1 minus 1. N is k minus 1 plus 1 minus 1 divided by x minus 1. X is 2 minus 1. Since this geometric series is applied, this is the sum of the first n terms in the geometric series. 1 x square etc. x power n up to x power n term. Now simplifying here k minus 1 and plus 1, what happens? The terms plus 1 minus 1 cancels. Plus 1 minus 1 cancels. So simplifying here, this is equal to n power. This 3 can be brought because 3 into log 2 base 2. Now log 2 base 2, right? This becomes 1. So in the next step, we write this as n power 3 into c. Okay, plus a into n square. Rest of the terms are 2 power k minus 1 divided by 2 minus 1 is 1. Simplifying in the next step, here log 2 base 2, this value is 1. So here we can write this is n power 3 into 1, so that we can write this is simply n power 3, n power 3, n power 3, n power 3 into c, or write c into n power 3 plus a into n square 2 power k minus 1. Since n is assumed to be 2 power k, substitute 2 power k as n, we will get n minus 1 whole divided by 1. So that results in, right, n minus 1. Now simplifying this result, we have this is equal to c into n cube plus an square is multiplied with n minus 1. We have a into n power 3 minus a into n square. So the recurrence relation T of n that we started here is simplified to this right hand side. C into n power 3 plus a into n power 3 minus a into n square. Left hand side is T of n. T of n is equal to this one. If we ignore this negative term, ultimately T of n is less than or equal to c into n power 3 plus a into n power 3. That means c plus a into n power 3. That we can write as something, a constant c1 into n power 3. Since T of n is less than or equal to c1 into n power 3, because in the termination stage, when n is equal to 1, we have applied equation number 2. Here we need to write T of 1, since T of 1 is equal to c from equation 2. When actual parameter n becomes 1, T of 1 value is c, so that c is replaced here. From this, we have the simplification as c into n power 3 plus remaining terms are simplified to have the quantity a into n power 3 minus a into n power 2. If we ignore the negative term, ultimately the left hand side becomes less than or equal to relationship. Now clearly T of n is less than or equal to some constant into n power 3. T of n is less than or equal to some constant into n power 3. This is compared with the definition of big O notation. Already we have seen f of n is less than or equal to c into g of n for all n greater than or equal to ng. If it's so, then we can write f of n is equal to big O of g of n. Clearly here, f of n is compared with the value of T of n. C, right, the constant, the C1 is there, n power 3, right, that is g of n. Therefore, T of n is equal to big O of n power 3. This is a cubic computational complexity. So the divide and conquer based matrix multiplication again results in a cubic computational complexity. Already we have seen the computing time of conventional matrix multiplication. Computing time of conventional matrix multiplication, that also results in a big O of n power 3, a cubic computational complexity. So clearly the divide and conquer based approach also results in the cubic computational complexity. So we have obtained the solution to the divide and conquer based matrix multiplication, That means the solution to this recurrence relation T of n is equal to 8 into T of n by 2 plus a n square. A is a constant when n is greater than or equal to 2, and C when n is equal to 1. The solution to this recurrence relation is obtained by applying the substitution method. Finally, we have got the result as a cubic computational complexity, order of n power 3. So clearly, the computing time of divide and conquer based matrix multiplication is order of n power 3 or theta of n power 3 in a time-bound notation. Conventional matrix multiplication also results in theta of n power 3. There is no improvement over the conventional matrix multiplication with respect to the divide and conquer based matrix multiplication. Both are producing the same computational complexity. So in this session, we have focused on what is the divide and conquer based matrix multiplication, how we are applying the divide and conquer based matrix multiplication, assuming that the input matrices are of order n by n such that n is equal to 2 power k greater than 0 integer, then only we can apply the divide and conquer logic to multiply the two matrices. Applying C is equal to A into B, right? Having Cij computations, we can find the product of A and B each stage. So subdividing each n by n, right, into n by 2 by n by 2, then n by 2 power 2 into n by 2 power 2, until we reach a matrix of order 1 by 1, such that n by 2 power k into n by 2 power k, we need to terminate a recursion. We have obtained the computational complexity of the divide and conquer based matrix multiplication as a theta of n power 3, a cubic computational complexity.